Hello, my name is Mary Gothen, and this is my presentation on carbonate mineralization. Carbonate mineralization, also known as carbon mineralization, is a process that involves the conversion of carbon dioxide, or CO2, into solid carbonate minerals, which effectively stores the carbon in a stable form. This process mimics natural weathering reactions that occur over geological timescales, but it is accelerated using various methods to sequester CO2 from the atmosphere. In carbonate mineralization, CO2 is reacted with metal oxides or hydroxides such as calcium oxide, lime, or magnesium oxide to form carbonates like calcium carbonate, limestone, or magnesium carbonate. These carbonate minerals can then be stored in geological formations such as basaltic rocks, where they remain stable for thousands to millions of years, effectively removing CO2 from the atmosphere. The process of carbonate mineralization has gained attention as a potential carbon dioxide removal technique, offering the promise of long-term carbon storage while utilizing abundant and relatively inexpensive materials. The CarbFix project, initiated by scientists in Iceland, is a pioneering effort in carbonate mineralization. Operating at the Hellisheidi geothermal power plant, CarbFix injects CO2-rich flue gases into basaltic rock formations deep underground. The injected CO2 reacts with basaltic minerals, forming solid carbonate minerals within a few years. This project, conducted by Reykjavik Energy and a consortium of international partners, including universities and research institutions, aims to demonstrate the feasibility of large-scale carbon mineralization as a carbon capture and storage solution. Initial results from CarbFix have showed promising rates of CO2 mineralization, with over 95% of the injected CO2 converted into carbonate minerals within 2 years. While carbonate mineralization offers the potential for significant CO2 removal from the atmosphere, it's essential to assess the environmental impact comprehensively. One potential concern is the use of metal oxides or hydroxides in the mineralization process, which may require mining and processing activities that could generate environmental impacts, such as habitat destruction and pollution. Moreover, the injection of CO2 into geological formations raises questions about the integrity of storage sites and the potential for leakage over time. While basaltic formations are generally considered suitable for CO2 storage due to their reactive nature, long-term monitoring is necessary to ensure the stability of stored carbonates and prevent any unintended environmental consequences. The technical feasibility of carbonate mineralization depends on several factors, including the availability of suitable geological formations, the efficiency of CO2 capture and injection processes, and the scalability of the technology. Basaltic rocks are particularly attractive for carbonate mineralization due to their high reactivity with CO2 in abundance in many regions worldwide. However, challenges remain in optimizing injection techniques to maximize CO2 conversion rates and minimize costs. Additionally, scaling up carbonate mineralization to capture significant volumes of CO2 from industrial sources would require substantial infrastructure investments and energy inputs. Continued research and development are necessary to address these challenges and improve the efficiency and cost effectiveness of the technology. Assessing the economic viability of carbonate mineralization involves considering both the cost of implementation and the potential economic benefits. While the initial capital cost of building CO2 capture and mineralization infrastructure may be significant, the long-term benefits of carbon sequestration could outweigh these expenses. One potential economic benefit of carbonate mineralization is the creation of carbon offset credits, or carbon pricing mechanisms that incentivize CO2 removal activities. Moreover, utilizing abundant and inexpensive materials for mineralization such as basaltic rocks and industrial byproducts could help reduce costs compared to other carbon capture and storage technologies. However, the economic viability of carbonate mineralization depends on various factors, including regulatory frameworks, market incentives, and the availability of funding for research and development. Continued efforts to drive down costs and improve the efficiency of the technology will be essential for its widespread adoption as a climate change mitigation strategy. Social and political acceptance is critical for the success of carbonate mineralization as a climate change mitigation strategy. Public perception of carbon capture and storage technologies, including carbonate mineralization, may vary depending on factors such as perceived risk, environmental impacts, and ethical considerations. Engaging stakeholders through transparent communication and participatory decision-making processes is essential to build trust and ensure that the concerns of affected communities are addressed. Moreover, governance frameworks for regulating CO2 storage activities and managing associated risks must be developed collaboratively with input from policymakers, scientists, industry stakeholders, and civil society. Given the global nature of climate change, international cooperation will also be necessary to address challenges related to cross-border CO2 storage and ensure equitable access to carbon removal technologies. Establishing clear standards and protocols for monitoring, reporting, and verifying CO2 storage activities can help build confidence in carbonate mineralization and foster its acceptance on a broader scale. Managing the risk and uncertainties associated with carbonate mineralization requires robust monitoring, risk assessment, and adaptive management strategies. Key risks include the potential for CO2 leakage from storage sites, adverse environmental impacts, and technological failures. Continuous monitoring of CO2 injection and storage sites is essential to detect any anomalies or leakage events promptly. This monitoring should include measurements of CO2 concentrations in soil and groundwater, seismic activity, and changes in geological formations. Furthermore, risk assessment frameworks should incorporate multiple scenarios and uncertainties to account for the complex interactions between geological, hydrological, and biological systems. Adaptive management approaches such as flexible operational protocols and contingency plans can help mitigate risk and respond effectively to unforeseen events. Ultimately, the decision to deploy carbonate mineralization as a climate change mitigation strategy must balance the potential benefits of CO2 removal with the risk and uncertainties associated with the technology. Regular review and evaluation of projects are necessary to ensure that they remain aligned with sustainability goals and minimize adverse impacts on ecosystems and communities. Carbonate mineralization shows promise as a carbon dioxide removal technique with the potential to contribute significantly to climate change mitigation efforts. However, its feasibility and viability depend on addressing various technical, economic, social, and environmental challenges. While research projects like CarbFix have demonstrated the effectiveness of carbonate mineralization in sequestering CO2, scaling up the technology to achieve meaningful emissions reductions will require sustained investment and innovation. Moreover, ensuring the social and political acceptability of carbonate mineralization will require transparent communication, stakeholder engagement, and robust governance frameworks. As with any geoengineering technology, carbonate mineralization carries inherent risks and uncertainties that must be managed effectively to prevent unintended consequences. By adopting a precautionary approach and implementing rigorous monitoring and risk management measures, it may be possible to deploy carbonate mineralization as part of a comprehensive strategy to address climate change while minimizing adverse impacts on ecosystems and societies.